in a lot of people.
Hey everybody, welcome to extreme video conferencing.
Hi Ed, good morning.
It is a spectator spot, so yeah, please mute yourself unless you want to talk, just because with this many people it kind of gets crazy. I think we'll just leave it a couple minutes just to have a few more people join and then end away.
I think they automatically join after.
Ed, wanna start?
Yeah, I think that makes sense. Thanks, Tatiana. Hi everybody, welcome. My name is Edward Lane, and my main reason for being here, kicking off this meeting, is I help set up collaboration and open source collaboration, particularly at Google. I'm going to be here very briefly just to welcome you all and kick things off, and then hand over to the project team. But in general, if you have any problems or issues trying to communicate, please just ping me and I can help you out and help everything go smoothly. We have a lot of people, and feel free, very free to ask questions and interact during this meeting. You can drop something in the chat in the Hangout, which we'll pick up on and read out, or of course, please just speak up at the right time. We know it's quite difficult on video conferencing, so dropping something in the chat, questions, is all good. We have a notes doc that I think was attached to the invite in this. If someone, Pankaj or Tatiana, you can drop a link to that in the chat, that would also be great for people to follow along.
I'll do that.
Thank you. So that has obviously our agenda. If you feel willing, it's compulsory, but to drop your name in the list there, just so we know who's here and how to get back in touch with you. Basically, if there's something interesting and a conversation we want to carry on, it's really handy there. And obviously, you can see who else is in the meeting. So if we can go back to the slides briefly. And move to the next one, thanks. So we're really excited to be able to open up the design meetings for MLIR, and the intent here is really to foster this open and collaborative community. I'm actually on the road right now at the Open Source Convention, so this is an ideal timing for us to kick this off. One of the kind of major vehicles in this meeting is that we'll be presenting design proposals and discussing them. And that's not just exclusive to the team. Obviously, in the room you see at Google, it's about everybody. And the process we're going to use is you can add things into the Google Doc to sign up for presenting things. We obviously have the mailing list, which, as you know, many of you are on, and it's incredibly active, and be able to sort of confer there and share ideas. There's a question that came up, say, would this recording be made available? Yes. All these meetings are public. The recording will be made available, linked from the notes doc as soon as we kind of get it after the meeting there. So with that, I don't know, Chris, do you want to also just talk a bit about your ambitions for this project and kind of for the open design meeting philosophy?
Yeah, absolutely. So as Ed said, welcome to everyone. I'm very excited about this. I think that, to me, large-scale infrastructure is best built by a community of diverse people, different kinds of backgrounds, different kinds of interests, different kinds of angles. And having that community, I think, is a really good way to make sure it's well balanced and it covers the different angles. One of the things we want with MLIR, and we'll be talking about this in a little bit, is for it to solve a wide range of different use cases and get used in lots of different technologies, both TensorFlow, which is our focus, but also a lot of other tools, technologies, frameworks, and other things. And so I'm really glad you're all here, and I hope that you participate, and over time, we'll be doing this on a regular basis. So I hope to see other people that are not on Google presenting and talking about their topics as well. So I think we can get into the main thing.
Let's just do the next slide, Tashana. Just a reminder, we have a code of conduct that we have for our communities here at Google, and you can read that. Basically, it sums up as, be a decent human being to each other. And so if at all you have any issues, please reach out to us. I'm particularly here just to help everybody communicate and collaborate productively. So thanks for that. I'm going to hand it now to Tatiana to move things on.
Okay, so these designs meetings are going to be about jointly designing MLIR. I presume that people on this call know what MLIR is. If you don't, please go on GitHub, look at the code, read the documents, watch recording of URL LVM keynote. That will give you pretty good idea about the background. In a few words, MLIR is the compiler, is an infrastructure for building compilers. We of course have LLVM, and that's fantastic as long as you want to build a compiler which operates on standard things like registers, control flow. Once you look at more complex system, like for example, TensorFlow, we have tensors, we have structured control flow, we have high-level operations which work on tensors. We need a framework which allows not only to represent and store these values, but also work with them, optimize them, generate efficient code from them. And that's one of the examples of applications of MLIR, because MLIR is a general framework for building compilers. It can be used to represent any high-level information, not just TensorFlow. And we really look into the community to find users which satisfy whatever they want to do. The difference between MLIR and a lot of other projects which say this is a unified thing to do something is that MLIR is really a compiler infrastructure. So for example, in machine learning space, there is ONNX. We are not trying to be another ONNX. We are not trying to standardize how to represent things. We are trying to build a framework which allows people to represent things. Basically, the crowd here has pretty good compiler expertise. So we hope that we build things right, but everything is in flux. We are learning as we are going. And again, we are looking to the community to add your expertise to try to make sure that whatever we build is the right thing.
Yeah, and I think just to plus one that we have a lot of expertise building different things, right? And so nobody's ever built something quite like this. And so the iteration, the change, how best to do code generation, there's many open questions. And so the folks that helped initially build MLIR have one set of experiences, but there's a much broader set of experiences spread across the community as well. And so we're really interested in getting to the world's best thing, and that requires a lot of different people, different backgrounds working together.
Yeah. Thank you, Chris. So if I have to give like a few sentences, technical summary of what is MLIR, ML stands for multi-level. That's the key. To build a compiler which operates with the higher level concepts, we need to represent those concepts. They come in all kinds of flavors. The key thing about MLIR is the ability to represent these concepts, which means that this is a multi-level representation. And that allows us, hopefully, to support a large variety of things, including code generation for the large variety of devices, which is the reality with what is happening in the hardware space today.
There's a question.
Oh.
Yeah. What is the process for updates to the public MLIR spec from the design meetings?
Good question. I would say PRs probably best.
So we don't have a formal evolution process at the moment. MLIR is still changing quite a bit, and it's still fairly early. We expect it to change quite a bit. And so the design of the dialect-based system, for example, each owner of each dialect should be able to define and evolve their set of ops the way they see fit and can define their own processes. I don't think we have a unified process yet. One thing I'll say is MLIR has this standard dialect. Nobody likes the standard dialect. And so we expect that to change or maybe go away. And so we'll evaluate that over time too. But I mean, there's a lot of good things there, but I don't think anybody holds anything in particular as a religious, immutable concept. We really do want to get to the best possible system.
So MLIR is open source, of course. We are accepting pull requests. There are standard TensorFlow process for doing this. The repository is actually two repositories. There is MLIR core, which is on TensorFlow MLIR, and then all the TensorFlow related code is actually part of the TensorFlow repository. We have mailing list, we have this meeting. If you have questions, ideas, please post. So we've been working on MLIR for a while now. We did some things. There are even more things to do. This is kind of a list of things that we are working on right now. The three major buckets are core infrastructure, code generations, and things related to TensorFlow. So for the core infrastructure, this is kind of deep dive. First one is declarative operations and pattern definitions. So one of the key features of MLIR is that you can define operations declaratively, and then we use TableGen to generate both documentation and implementations. You can define patterns. There is a lot of work to be done to make the system full-fledged and having all the capabilities that we want to have there. One interesting challenge that we encountered is unifying operation properties across dialects. So being a multi-level system which supports any dialect is great. The challenge is that if there is absolutely no common properties of operations across the dialects, it's hard to write optimization process which are reusable across the dialect. So we are working on the operation traits mechanism, which will allow to abstract properties of the operations, which would allow to write generic optimizations process, which basically deal with operation properties rather than operations themselves.
Can I give an example? So for example, an inlining pass can be a generic pass, but it needs to know what the calls are.
Yeah.
And the calls can be represented in arbitrary ways. They support a certain protocol or a certain set of operations. And so that should be definable orthogonally from the MLIR pass.
So the RFC for this is going to be coming up at some point. Mehdi, do you want to talk about function and modules as operations?
Sure. I mean, we sent an RFC, I think it was 2 months ago. Oh, River is here. Also, we sent an RFC on a mailing list a while ago about this change. The idea is that we wanted to make DIR more regular and not have function as much as a first-class concept as they are today, which open up the possibility to create your own function abstraction. And so I think all the changes are landed now. There are still a few minor cleanups to do, but basically this has been implemented. And so a module is a list of operation now and no longer a list of function. And we will be able to define top-level operation inside a module that are not function or that are dialect-specific equivalent of function. Whether I think right now we're looking into LLVM globals and other kind of global constants.
Do you want to say anything, River? I mean, come closer to the mic.
One other nice aspect is that you can actually compose multiple modules within a single module. So you could, for instance, slice your module into another module that has a couple functions and actually cogent that differently than how you would the rest of the functions within your big computation.
So you could have code for two different devices in the same unit of IR.
Yes, for example, you could say, I'm going to move these functions to a different module and then call into the cogent for CPU. And then all of that lives within the same, I guess, top level module.
Which is great for offloading and other kinds of use cases.
Yeah.
Things that LLVM's never really been great at.
So hypothetically, you could multi-thread compile multiple different devices within the same run of compiler.
Okay. So the next one is multistage dialect legalization. Can you talk about that?
Sure. I think
why don't we just give like a high level TLDR kind
Yeah,
of,
like
okay,
kind of summaries on this?
So dialects can represent different sets of abstractions. Tatiana mentioned TensorFlow, but also LLVM and XLA. So generally in compiler infrastructure, you have to have this big monolithic process to go from one representation to another. But since in MLIR, we can represent all of that together, and we actually want to intermingle dialects. We want this general extensible infrastructure to actually allow lowering between different dialects. And sometimes, I don't know how that plays.
So instead of just learning from A to B,
yeah,
often you want to go A to B to C. And once you do that, you can handle scalability across many different. I have lots of inputs, I have lots of outputs, but you need to define a common funnel point so that you get reuse across these lowering patterns.
So basically, we have the capability of loading from one set of operations to another set of operations. We want to have the framework which can find transitive paths by itself. So if you have A to B and B to C, you don't need to define A to C. The next thing is side effect modeling. Some operations have side effect, and to build the compiler which operate with them, we really need to add to MLIR the capability to model side effect. That's especially important if you want to look into executing things concurrently and go in between different representations, like, for example, data flow graph versus just a sequence of instructions going back and forth. It's important to know which instructions can and cannot be run concurrently. Quantization is a very interesting feature, and we will have one of the meetings devoted to the whole topic of how do you represent quantized types, quantized values in MLIR and build optimizations which operate with them. We have interesting work going on. Okay.
Okay, sorry. I don't. Okay. Can you elaborate on why quantization is bundled as part of the core infrastructure? It seems more domain-specific compared to the rest of the items listed in the core.
I don't think there is a firm opinion here or firm desire to put it as part necessarily of core. I can easily envision that, like the current division of core code generation TensorFlow is going to have many more buckets. It is part of the core repository right now because it's not specific to TensorFlow. Beyond that, it might be a separate bucket of things which are, for example, important only for machine learning domain.
Yeah, I mean, I think one of the things I'd underscore here is that just because there is a quantized type in the repository, the entire design of the system is that people can introduce their own abstractions. And so if you have a different representation or a different way of doing quantization, that's great. That can live side by side with the existing system, and it's extensible enough that you can do that. And so I wouldn't be surprised if we end up with multiple different approaches and multiple different theories and philosophies on what quantization is. On the other hand, I think it's good for us as a community to kind of eventually pick a winner, or pick a winner or two, maybe, but not 10, because yes, we need to interoperate with all the things, and so we'll end up having a lot of that complexity of the world, and we need to factor that, but we want to be able to invest in specific opinionated paths as being the right thing. I don't think that our design is necessarily the right thing. There's been some discussion on the mailing list, and it's kind of a prototype at this point. So don't over-index on that and don't worry about that. And so if you think it's wrong, then please help make it right.
Can you please read?
Yeah, I think it's.
Oh, that's okay. Okay, good. So code generation. This is pretty much work in progress. There are many different ways to do code generation. There isn't like the right way and the wrong way. There are just many different techniques. We are building a code generator right now, basically based on linear affine dialects. We have implementation which supports polyhedral techniques with affine dialects. We have memref representation. A lot of these things are in flux. So for example, there is discussion on the mailing list. We are working on redesigning the memref representation, and one of the meetings will be devoted to that. We have two distinct projects going on for code generation for GPUs. So there are folks who are working on GPU and NVVM dialects, and then there is folks who are working on Spira-V dialect, and it was great to see contributions from the community to Spira-V dialect. Some of our efforts are on TensorFlow, obviously. This is not part of the core MLIR. This is something that we are building on top of MLIR. There are a lot of interesting work to be done there. So first of all, if we want to work with TensorFlow graphs, we need to represent them in MLIR. We have posted the RFC for how do we represent TensorFlow graphs. This is done using two dialects, TensorFlow executor dialect and TensorFlow dialects. And again, there will be a presentation which talks about that. Our plan is to effectively rebuild everything in TensorFlow which relates to compilation in the most general sense of word using MLIR, which means that the compiler that we are building will subsume any existing components which work with compilation, for example, Grapla or HLO optimizer. We are building a conversion tool from TensorFlow to TensorFlow Lite. This is basically the first practical applications. It's relatively easy. This is just dialect legalization. We go from TensorFlow dialect to TensorFlow Lite dialect. This is almost ready. We hope we'll put this actually to real use with real users by the end of the quarter. We are working on rebuilding what is currently known as TensorFlow XLA bridge using MLIR. The component that we are building is going to be more general. So we are trying to basically build a general component which allows you to take part of TensorFlow graph, extract it from the graph, lower it to a different dialect, replace it by some operation which allows you, for example, to call XLA, or any other third-party system which might take XLA as its input, or might take its own dialect as its input, or might take combination of any operations from the existing dialects as its input. And the intent here is to build a flexible tool which allows you to basically reuse this functionality across the large number of systems who want to integrate with TensorFlow, including XLA.
So then there's a question. For TensorFlow XLA dialect, is it possible to reuse the existing XLA HLO optimization process or not?
Existing XLA HLO optimization process, yes. So the way this works is that we are trying to build as many ways to interoperate between MLIR and TensorFlow as we can. Just to introduce the terminology, we use the term translation to say we translate, say, between XLA and XLA MLIR dialect. And we have the ability to basically go from XLA from HLO to XLA dialect and MLIR and back. So you can do things in MLIR starting from TensorFlow. We produce XLA dialect. You emit HLO. You go into the current existing XLA compiler.
If I may interject here, there is a project that is starting to go down from XLA dialect of sorts after running XLA transformations to MLIR code generation. So that should be available relatively soon. And given that both XLA and MLIR are open source, it will go through open source mailing lists. That may go to both MLIR and XLA. So if you're interested in those, please keep track of those.
But I think there's a higher level point here, which is the general approach we're taking with TensorFlow, and we're using MLIR to do this, but the general approach we're taking with TensorFlow is to upgrade the core. And as part of doing that, we're keeping all the systems and then upgrading chunks of them in place. And so XLA is an important part of the TensorFlow ecosystem. We're not planning on replacing it or dropping it. And if you're investing in XLA, that's a safe thing to do. But we also want to step way beyond that. And so we're working today on improving the core part of TensorFlow using MLIR and other technologies. But we also have ambition to go way beyond what TensorFlow currently does over time.
So the follow-on question is, so the process is that we provide bidirectional conversion support between XLA dialect and the HLO representation. Is this way the existing HLO passes can be reused?
Yeah, so you can definitely reuse the existing HLO passes, and we use XLA both for GPUs, also for TPUs, and a little bit for CPUs as well. The general way we structure this is that we see XLA as it's a compiler, just like TensorRT and ngraph are conceptually within the TensorFlow ecosystem. They're compilers with their own IR, and so HLO is XLA's IR. And so the TF-XLA bridge is a lowering from, the A is TensorFlow nodes, the C is HLO nodes, and then we can introduce our own intermediate abstractions there if we choose to. And so nothing in the upgrading of the bridge means the XLA itself has to change. Now, separately from that, we want to improve code generation. We want to make dynamic shapes easier to deal with. We want to make custom ops easier to deal with. We want to make it so that TensorFlow can deal with non-dense data types better. There's a bunch of other work on that. And so we both want to work with the existing systems, and we know that our customers have our partners have a lot of existing technologies that plug into TensorFlow in important ways. We don't want to break that. We also want to be moving beyond the current technologies there.
Next question, is source-to-source code transformation something MLIR can be used for? Is MLIR ideally an internal representation along the path from source to executable?
Does anybody want to talk about that? I can, but I'd rather not monopolize the conversation. Do you want to talk about like Toy, for example?
Just for high-level presentation.
I think the question is about sources. I only know what the question says, but I don't think that MLIR is probably the best thing to use for source transformation.
I mean, it could, like, if you were to implement a full SIL, like a full, very close to the source language compiler, you could probably do that. Now, I don't know. I haven't really considered it. Like, source-to-source transformation is challenging. It means like you have to be able to regenerate source code, and depending on, it depends also on the use case. There are source-to-source transformation where you want to have like human readable code, or you want to do like refactoring of your code that will be maintained by a human, and there is like just you want to regenerate code that another machine will use, and they have different trade-offs. I think MLIR could be used for that, but
I think it's fair to say we don't know.
We don't know.
Yeah, so that's not been a focus. We don't know. Maybe, but I don't know. It'd be interesting to explore.
Any more questions?
They want to know this on the XLA side, if there is any code snippet in the TF MLIR GitHub to demonstrate how this will actually work. Can you send something?
How integration with XLA can work?
Yeah, so just yesterday we open sourced the tool that allows to import from HLO, from the HLO XLA representation into the XLA dialect in MLIR. But all this work is still very early and also very much work in progress, but it's going to evolve a lot in the coming weeks and months. But there are already if you look in the test folder, you can see test exercise importing HLO and
No,
generating the
I think the question was the other direction about like export and XLA dialect.
It goes in both directions. I think the tool has the ability to go from the dialect to HLO on that direction.
Yeah, that's it.
Okay.
So, okay, I think I went through most of the things on the slide. The only other ones is generic shape inference. We want to support dynamic shapes. Basically, we have to support dynamic shapes if we want to use the infrastructure to implement general optimizations on TensorFlow graphs. To do that, we need shape inference mechanism, and we are working on it. And finally, a very important part of optimizing machine learning models is mapping them to parallel and heterogeneous hardware. And so we are working on generic mechanisms for device partitioning and parallelism. Let's see. These meetings will be weekly, and at each meeting we will have a presentation about a particular topic. So this is a kind of very tentative preliminary schedule. Hopefully, as things move along, we will have things more definite. We don't want to be the only people presenting in these meetings. So, and the discussions are definitely not limited only to things that we are working on. So please sign up to present. And the first step to do this is submit an RFC to the mailing list. And then you get a slot to talk about that RFC.
Or just ask on the mailing list. I mean, I think it's like we really want to foster a collaborative community, and so just sending an email to the mailing list and say, "Hey, I'm thinking about this thing. What do you think?" It's totally fine.
Yeah. And basically, this is meant to be open design meetings. It's a little bit hard because this is GVC, but we hope that this is not going to be one-way communication of us presenting to the community. We're really looking forward to kind of open the design process and hear from other people who are working with MLIR. How would you like to evolve the project and what you are doing? Okay. So
yeah, we're short on time, so I'll quickly go through the next couple of slides.
There's a question.
A question.
As to dynamic shapes, a question is that for XLA HLO, currently it doesn't support dynamic shapes natively. So how do we ensure that MLIR dynamic shape mechanism can be fully supported in the XLA dialect?
We're not looking to generalize the XLA dialect right now. Support dynamic shapes. We're talking about generic support across, for example, the TensorFlow dialect. That needs support dynamic shapes. But this is something we'll continue evolving over time. Why don't we keep going?
Yeah, so on the community side, it's great to see the traction, guys. So appreciate all the folks who have been contributing. The couple of things that we want to highlight is Flang, the compiler. They've been looking at MLIR as a way to, they're investigating at the MLIR dialect. That's something neat. The ngraph team is also working on a dialect with using the MLIR. So thanks to the ngraph team. There were some meetups where MLIR came up in Tokyo, so that's gratifying. And as you can see, people have already started contributions and we've been accepting them. I think this one's fine. You can just do that. I think going next, we can start on the design topic.
Actually, I wanted to make a comment on community highlights. So if you are working on something using MLIR, please let us know, right? Just like post on the mailing list, hey, I'm working on this cool thing, take a look. Because that allows other people to be aware of great things that everybody's doing. Okay, so now...
There was a question on the...
We are interested in doing the following MyIR to MLIR to LLVM transformation. Is this something we can do? In general, we are interested in the affine dialect. Do we have to analyze our loops to figure out if it is affine before using that dialect? Or is this part of the invariant check?
I think this is a detailed enough question that's best to bring it to the mailing list right now, just so that we can keep making progress in the topic here of the day. But please do ask on the mailing list. That'd be great.
Okay, so
gonna let Andy to talk about MLIR tensor layout proposal.
Okay, can I
Yeah.
drive? Thanks,
Yes.
Tatiana. Okay, so I'm here to give a talk about adding an optional attribute to an existing MLIR type, the tensor type. So the rough agenda here will be give a little bit of background, then motivate a proposal. I'm going to take a little bit of a little time to explain one option for layout. This is not the only option. So as I mentioned, we're proposing adding a layout attribute, which means people can create their own attribute for layout and use that internally inside their dialect. But I thought it'd be worthwhile to talk about one layout that we use internally and that we're going to support as part of the proposal. Then I'll go into the proposal, and then we'll hopefully have time for questions at the end. So background, I think hopefully most people know this. Maybe some people don't, but it's always good to go back over things. So what's layout? Layout, I like to think of it as a mapping from a logical coordinate space to a physical memory space. So if you look on the left-hand side, you see a logical coordinate space. That could be a matrix. This could also be a multi-dimensional tensor. Here we only have 2 dimensions on the left-hand side. And through this linear index function, we map it to a linear address space as follows. So this is, people will recognize this as a row major layout. When we start getting into multi-dimensional arrays, then we need to specify layout, and there's lots of different ways to represent that. So let's go to the next slide. So what's our motivation here for adding it to the tensor type in particular, right? So as some of you may know, in the memref type, we already had layout. So why are we adding it to the tensor type? Well, here's our motivation. So the world sort of starts with, if you think of the world starting with a graph of tensor operations, it goes through different levels of lowering. And at one phase, you've got a partition across devices. And so you may have partitions of the graph go across different devices, or be partitioned between a host and an accelerator on the same device. And you need to have agreement on the layout when you communicate tensors across these boundaries. So a lot of times, between different hosts, you're going to have send and receive tensor operations, and you need to agree on layout in these type of situations. So that's one motivation. Another motivation is our internal systems like TensorFlow and also XLA do whole graph optimization layout assignments on tensors. So before they go to code gen and expand the number of ops greatly, they do these algorithms that go over the graph and will assign layouts to operations that operate on tensors. Some of these will start with, like in the XLA case at a high level, it'll start with some of the more constrained operations whose performance is really dependent on layout, like convolution or mapmul, and then sort of propagate that layout to operands and downstream users in the data flow graph. So that's another motivation. We want to be able to support that. Also in many cases where you're progressively lowering down to library calls. So you'll see that on the XLA CPU and GPU backends, where we call PUDNN and MKL respectively. So in those cases, obviously you need to, there will be supported layouts that the library can handle, and you need to either potentially change the layout of your tensor before you pass it into the library, or make sure that your layout assignment algorithm knows what the possible layouts are and does the right thing at the beginning. So we want to support library calls and proper layouts for library calls. Also in XLA, we've found it useful for a couple of reasons to separate the logical dimensions from the physical dimensions. And that's sort of the separation I hinted at in the slide here. So for tensor operations, there's value in this separation, and you can change the layout without having to change the sort of indexing in the logical coordinate space. And of course, we also want to support custom internal layouts. So we're not, as I mentioned at the beginning, we're going to talk about the XLA tiled layout, but we don't expect we're not trying to force everyone to use it. We want to be flexible. We want people to have their own internal custom layouts in their own dialects and support those. So these are just a couple examples that we've seen in our experience, but there's there's many more out there, and we want to be flexible enough to support custom internal layouts as well. Okay, so let's take a little side trip and talk about the XLA tiled layout. So as part of our proposal, we want to add some support for this. We're going to potentially make some small changes to this, but I wanted to go over it just as an example. So some of you may notice we're starting to conflate a couple of different operations here. So back in this slide, this was pure layout, right? It's an index coordinate space transformation, right? So here, now we're talking about tiling, layout, padding, arguably reshape. So this is an intentional conflation of these things to get a succinct description for layouts that we find valuable in the XLA world. It could be possible to do these as a sequence of ops in some cases. In some cases, that's difficult at boundaries between compilation units and things like that. Okay, so what do we have here? Let's go through the syntax a little bit. On the left-hand side, you'll see sort of the logical coordinate space. And this is a two-dimensional tensor of float 32s. So the first dimension is size 3, second dimension is size 5. And we're going to tile it by 2x2 tiles. So this is going to first tile each dimension by 2 elements. And you see these clear elements here are implicit padding that is added. So that's part of what I was talking about before, which is the intentional conflation of these two different operations in this layout specification. Then you can see the other part of the specification is the logical dimension permutation. So this says that it's specifying that dimension 0, which is the dimension size 3, is the slowest varying dimension. And dimension 1, 5, is the fastest varying dimension. So that's going to map to your stride 1 dimension and potentially vector registers and things like that, right? So this permutation here specifies of these logical dimensions, the ordering from slowest varying to fastest varying. So you can see as a result of that, as a result of the spec, the shape with this layout is tiled by 2x2. And so this is what the internal memory representation looks like with the padding included in there. So this is layout, tiling, and padding. Okay, hierarchical tiling. So this is useful when you have multiple levels of memory hierarchy, which we all do. So XLA's tile layout also supports that. I didn't show the full string to specify this. You can see that later in the proposal. And also, I forgot to mention this at the beginning of the talk, but I sent out a document describing this on the public MLIR mailing list a week or two back. So there's more details and links in there. So you can find a link that describes the XLA tile layout from a document on GitHub if you want to get more details.
There is a question, Pankaj.
Oh.
Is the current layout proposal support allocating data in a distributed system?
So I think that's a system level concern when we start talking about partitioning and device placement and things like that. This part of it is just talking about, given a specific value that has tensor type, how is the data within that tensor laid out in memory?
That's right.
It's not trying to do distribution or things like that.
Right.
I mean, you could have other passes that come and say, this is a very large convolution, let's do spatial partitioning or something like that.
Right. And a device partitioning pass would need to make sure that operations that communicate between partitions agree on layout.
But there's also nothing forcing the tiled layout to have any particular correspondence to. There's no saying how you do virtual address mapping on your machine. So you could say that like this is your virtual address space, and you can split it up onto different machines in some way using the tile layout.
One of the levels of your hierarchy of your address space could be machine.
Devices.
Yeah.
How do sparse and block sparse tensors fit into this?
I think these layouts are index permutations. And so conceptually, you could do something with sparse layouts here, but I think that I don't think this would be the necessarily right way to do sparse layouts. As Andy mentioned, the design here allows arbitrary MLIR attributes to be used as layouts. And so this is one layout, but having a block sparse layout or having a custom layout or having NCHW as a layout or having other things like that is also perfectly fine. And so this is a certain class of devices and a certain class of dense data types can use this, and that's great. But I think that it's not trying to be the one solution for all problems.
Right, that's right. Right, so there are ways. So you know, in the design of this, we had a spec for layout that used affine maps, a composition of affine maps to express something like this hierarchical tiling, which is doable that way, but it's also a little bit more succinct in this form, where you know, the initial tiling reading from left to right is 2 by 4, and then within that tile you tile 2 by 1. Okay, so what's the proposal here? The first thing we want to do is add an attribute value to the MLI tensor type for layout. And this will be added, this will be optional, so it's not going to break existing tensors that are out there. Also, when you look back to the, you know, to that world where you've got a graph of tensor operations that you're going to optimize, really early on in the graph, you don't want to constrain things by assigning layout too early. So there's going to be multiple transformation passes on HLO graphs or tensor operation graphs before you get to a point where you're going to assign layout. So that's another reason we'd want it to be optional. The other part of the proposal, as I mentioned earlier, is that we're going to leverage this tiled layout work from our XLA team and add that as one of the layouts we support. The only thing we're going to change a couple things here. The layout permutation. So if you look at the XLA code in the public repository, you'll see that the layout permutation goes from I believe it's most minor to major. We're flipping that to major to minor, which made a lot of people around my desk just cheer, and a lot of people like to think in row major. The other one is to add this memory space here. So this is part of the layout. You'll see that I think also has been added recently, part of the XLA layout, if I'm not mistaken.
We'd love to make that more symbolic, you know, so you could say, you know, refer to different levels of your memory hierarchy by symbolic names, but numbers are
where we're at now.
Yeah,
that's
numbers
right.
are the state of the art at the moment.
Right. So what would this look like inside an MLIR tensor type? So the first part, the shape part, is you know, what you see today, and then one proposal. This is sort of the working proposal right now, is to have the tile layout attribute look like this, where you'd have the layout permutation, the tiling permutation right here, and then the memory space at the end. And so I think as we formalize that and decide once the work becomes more concrete, we'll update the public specification on that. But again, as I mentioned in the beginning of the talk, this is just one option. We wanted to highlight it because we find that it's a useful way to specify layouts, and we're going to use it. But it's an attribute, so you can create your own layout as you see fit. So now we have time for questions, I guess.
Should we share the proof of its universality? Like we have an internal proof of its like universal linear index transformation. Probably should include that in the documentation.
That'd be awesome.
It might be in the public doc. So I had sent out like a public document on MLIR list, and there's also a public tile layout doc in the XLA GitHub repository. So I don't know if the proof's in there, but
I don't know
if you're interested in sharing it, that'd be great.
Yeah.
So the question, there's one question: Are logical dimensions 1-to-1 with tile dimensions? Can you split a logical dimension up with tile layout? In other words, can you have a 4D tile with a 3D logical dimension?
Yes, you can split a dimension with tiling in arbitrary ways, essentially. You might have to add a lot of dimensions of tiling to do very fancy things, but you can completely represent any shape represented as another shape with the tiled layout.
Is tiling allowed to be dynamic?
There's no support for dynamic tiling yet, but theoretically there's a star type dimension, which means everything, and collating it together, so that would technically take an entire dynamic dimension if the dimension were dynamic.
So there's a link and they say, I see this proposal has a suggestion to expand this syntax. Does MLIR have a formal grammar defined beyond what's outlined in GitHub, blah, 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 lang ref.md?
I think that's the best we have.
Yeah, I think that's the syntax, and then this is the sort of working proposal at this point. It's not more concrete than what we have here.
So we have 6 minutes left. Should we go back to the agenda document? I think we have a bunch of questions there. Should I?
Yes, thank you.
The first one, I'm just picking up randomly. The
There was
code in
another question on the
I'm sorry.
Tensor layout.
I have them here. The code in the MLIR repo and the TensorFlow repo are out of sync from time to time. It's a bit annoying.
Yeah, I can take this one. We're
Yeah, try to
we're fixing this with tooling these days. We're just going through bugs on the tooling side, but it should, like, the goal is to be fully automated and always in sync, etc., etc. It's just like scripting and.
Do you have an
and going
idea
through
of
it
how
and
long
so-
that would take?
I don't know. Is Christian on the line or somewhere? I don't know. Maybe this week, maybe next week. But it's like before the end of this month, everything should be always in sync.
Principles for driving evolution of code generation module of MLIR, more principle polyhedral based approach or more practical TVM-like approach?
I think the answer is yes. We're not quite prepared to talk about what we're planning right now, but we're trying to put infrastructure in place that allows retargetable declarative code generation, lowering of HLOs to code, right? And TVM and PlatML and Halide all have roles to play in that.
Yeah, I think if you look at the project overall, the project has two different approaches, right? One is embrace heterogeneity and different kinds of ops, different kinds of accelerators, different kinds of things will want different kinds of code gen algorithms. And so that's just inherent. And in the increasingly heterogeneous world we have, that's gonna be a thing. And beyond that, we have software, and not all software wants to change completely every day. And so even if there can be different techniques, sometimes leveraging an investment in a technology is a good thing to do. That said, we want to pick a few specific techniques. Like, it would be great if we had one primary path to CPUs or one primary path to GPUs, for example. But if an FPGA-based backend wants to be completely different, then okay, that's fine. Or if it can leverage some amount of code somewhere, that would be great.
Principles, status update on optimizations in the development in Affine and Ling-Al dialects from Google.
So
I guess I can take that.
Yeah, please.
Yes, so basically we're trying to, so for those who do not know, there are, I think, at least two different passes it can take. One goes from what we call linalg. It started as linear algebra, but it's basically an HLO-like representation of operations that we know about, like tensor contractions and convolutions that don't necessarily need analysis to be transformed. And there is polyhedral or affine passes that do the analysis and do the same kind of transformation. So what we're trying to build is infrastructure where you can apply loop transformations such as fusion, tiling, interchange, skewing, so on, usual loop stuff, with analysis results coming from either affine analysis or being defined by construction of the operations that come from higher levels like TensorFlow.
Yeah, and I think one of the tricks here is that we're coming from an implicitly vectorized and implicitly parallel form. And so we want to be able to lower down to hardware without kind of throwing away information and then trying to reconstruct it back later.
Right. And one more thing I'll point out on the difference between these two dialects too is that Affine has dependence analysis and footprint analysis, things that operate on arbitrary loop nests. So for custom ops or things that don't where the semantics aren't known, as like as a domain specific op, like a MAML or a comb or something like that. For that path of operations, we'll still have a way to kind of hopefully optimize it, even though we don't know what it is, and still have a good story on performance.
2 minutes left.
I think the last question, Mehdi, do you want to take this? What will be the dependencies of on MLIR be in the long run? XLA bundles LLVM, which causes serious problems for packaging on distros. Will MLIR be completely upstream to LLVM? So TF just needs to.
So this is a question that is from a TF point of view, I think. When I read the end, MLIR depends on LLVM, of course, just like XLA does. I'm not sure what packaging problem there are.
So basically, I wanted to know like how is it going to be built in the longer term? Like, is MLIR going to need to be in it? Is it going to be a separate thing that Tensor uses, or like?
Yeah, so I mean, I think it depends on if you're talking about MLIR as an open source project, or if you're talking about TensorFlow as an open source project, and what does it mean to build TensorFlow? MLIR in MLIR core is itself a standalone project. It depends on LLVM, and you can't build MLIR without LLVM. So it depends on it for the LLVM support library, and if you do code generation, then it depends on it for LLVM IR. TensorFlow depends on MLIR increasingly. And so that means that to build TensorFlow, you now need to build MLIR and you need to build LLVM, and the build instructions for TensorFlow make that easier and will be easier and easier over time. So I don't know, does that answer the question though? I mean, is that what you're really asking?
Well, will it always need to live ahead like XLA does? Or will there eventually be some point where like right now it's LLVM 8. Yeah. Is there a chance that like TensorFlow will use that, or is it gonna like, because shipping like head releases and distros is not really a thing?
It's very exciting. Yeah. I don't think we have any plans to change that, but we can talk about that offline. There's also a SIG about building TensorFlow, and maybe that would be
I'm the lead.
Oh, okay. Well, there you go. So
yeah,
that's
the question.
We don't have any plans to change it right now.
So we are out of time, and I think we went through all of the agenda. Thanks a lot for joining us. If you have any additional questions, please just post on the mailing list, and we see everybody a week from now. Thank you.
Yeah, thank you, everyone.
Thank you.